Kp and Kc are mathematically related to one another. Once again, Kp is an equilibrium constant done with partial pressures, whereas Kc is an equilibrium constant done with concentration or molarities. Mathematically, these two are related using this equation. Kp equals Kc times the quantity RT to the delta N power. Several of these variables are familiar. So Kp and Kc, we went over what those are. R is the gas constant. And the reason the gas constant and temperature are used here is we're converting moles per liter to ATM, which can be done via the gas constant. The gas constant that we're using here is 0.0821. If you care about the units of that gas constant, they're liters ATM per mole Kelvin. And the temperature that we're using here is going to be in Kelvin. You haven't seen delta N before, not in this case anyway. Delta N is going to be the change in moles of gas in the balanced reaction. So let's take a look at a couple examples where we have to find delta N, and we'll see how it works. So I'm just looking at moles of gas, and the G means gas. For this reaction, on the left-hand side here, I have 1 plus 3, or 4 moles of gas. On the right, I have 2. From 4 to 2 is a decrease of 2, so we are given a reaction that has a delta N value of -2. Therefore, if I were using Kp to get to Kc or vice versa, I would be plugging in a -2 for this term. Okay, take a look at the second reaction and think what you think it should be. We're going from a solid to a gas and a gas. We have 0 moles of gas over here and a total of 2 moles of gas over here, giving us a delta N of +2. Third reaction, how many moles of gas do we have on the left? 2. How many moles of gas do we have on the right? 2. So we have a delta N equal to 0. I want to remind you, you only count the moles of gas. So in reaction B here, I counted 0 because this wasn't a gas, it was a solid. Okay, now that we know how to get to delta N, let's look at an example problem. This reaction, 2NO plus O2 goes to 2NO2. We have Kp, which is 1.48 times 10 to the 4th. We have a temperature, and we want to find Kc. So first I'm going to take a look at delta N. 3 moles of gas on the left, because 2 plus 1. 2 moles of gas on the right. Delta N is -1. My temperature is in Celsius. I need to convert it to Kelvin. So 184 plus 273. 184 plus 273 gives me 457 Kelvin. And now Kp equals Kc times RT to the delta N. So 1.48 times 10 to the 4th equals Kc, which I'm solving for, times 0.0821 times 457, only that quantity raised to the -1 power. Solving for Kc, 1.48 times 10 to the -4th. Now, remember, if it's in the -1 power, it's in the same as in the denominator, or I can divide by the quantity, 0.0821 times 457, raised to the -1. And this gives me a Kc value equal to 0.00555. Okay, the second example is a bit more complicated because first we have to find Kc and then we're going to find Kp. Additionally, they gave us some information about equilibrium, how many grams of each one are present. If you want to try the problem and then pause and come back and look for the solution, great. If you want to just go through it with me, that works too. Okay, so if I'm going to get Kc, my equilibrium expression is going to be the concentration of PCl5 over the concentration of PCl3 times PCl2. I need to get the molarities of each one in order to plug them in. I have 0.105 grams of PCl5. I'm going to need to convert to moles, and then I'm going to need to convert to molarity. I've already figured out the molecular weight of PCl5, and it is 208.5. So dividing this by 208.5, 0.105 divided by 208.5 gives me 0.000504 moles. And then to get to molarity, I'm going to need to divide by liters, divided by 2.5, 0.000201 molar. I need to do this for each one, for PCl3 and PCl2 as well. We have 0.220 grams of PCl3. It has a molecular weight of 137.5. 0.220 divided by 137.5 gives me 0.0016 moles. And then 0.0016 divided by 2.5 liters, 0.00064 molar. All right, for the Cl2, we have 2.12 grams. The molecular weight of Cl2 is 71. 2.12 divided by 71 gives 0.0299 moles, divided by 2.5 liters to get molarity, 0.0119. I have each one of the molarities. Now I need to go back and plug them into the correct place in the equilibrium expression. PCl5, I believe, is on top and the other two are on the bottom. So PCl5, 0.000201, let me double check that, over 0.0064 times 0.0119. And we had no exponents in this problem. There were no coefficients in the reaction. So giving me Kc, 0.000201 divided by 0.0064 divided by 0.0119 gives me 2.64 for Kc. I've solved A. B, I now need to solve for Kp. This is going to be a lot easier. If I wanted to, I could go back and find the partial pressure of each one and plug it into an equilibrium expression, but that's going to take a lot of time. I'd rather do this. Kp equals Kc times RT delta N. Kc we just found. R is 0.0821. I'm going to need to go back up to the top and find out the temperature, and I'm going to need to look at the reaction again to get delta N. Temperature, 250 degrees Celsius. 250 degrees Celsius plus 273 gives 523 Kelvin. So we can plug that in. And I need delta N from the reaction. We have 2 moles of gas on the left, 1 mole of gas on the right. 2 to 1 is a -1. So 2.64 times the quantity 0.0821 times 523 to the -1 power gives me a Kp equal to 0.0615.